welcome to Lecture 10. Today we'll be covering the period from 1855 to 1884. The first and most important innovation of this is the appearance of the ironclad warship. There were a few things that had motivated this. One was that improving metallurgy over the past decades and couple of centuries allowed for heavier and heavier and heavier naval guns. These are examples of 36-pounder naval guns from the 1700s, and when you have 100 36-pound shells coming at you, that's a significant amount of firepower, so you would want to protect your ships with more and more timber. But eventually you cannot keep on using more timber because it just gets too heavy and too thick and too bulky. Also, the Poison gun, which we covered in the previous lecture, developed in 1824, was the first gun that gave ships the ability to fire explosive shells on a flat trajectory. Previously, explosive shells were only available for low-velocity mortars and fired on ballistic trajectories, but it's very difficult to hit a moving target on a ballistic trajectory, and earlier guns were unable to fire explosive shells because explosive shells were too weakly built, and if you try to fire them out of a regular long gun, they would just detonate within the gun itself. So Poison came up with the Poison gun, which was somewhat shorter and used a smaller powder charge, and also a stronger built explosive shell, and this was the first gun that was able to fire an explosive shell on a flat trajectory. And at the Battle of Sinop in 1853, the Russian Navy used Poison guns with explosive shells to extraordinarily great effect and took out an entire Turkish fleet in the Turkish port by storming into it. So after that battle, most of the world started thinking that you need to come up with a better protection for your ship than just some wooden sides. Iron has actually already been used in shipbuilding for some time, but by this point, in 1787, John Wilkinson launched the iron barge Trial. That was the first ship that used any iron in the design at all. And if you remember from earlier lectures, this was also the iron engineer and industrialist who came up with a method to bore cannons out of iron. So he did a lot of things with iron, and one of the things that he also did was launch the first iron-built ship. In 1819, Thomas Wilson designed and built the Vulcan. This was the first all-iron ship. So whereas the ship built by John Wilkinson had a wooden frame and just iron incorporated into the structure, this was the first ship that was built from iron directly and did not use wood in the construction of the hull. It was a horse-drawn passenger barge for some canals in Scotland, so it wasn't expected to be either very big or very sturdy, but it was the first example of making something that floats completely out of iron. It was 20 meters long, and as you can see from the picture, it was built from iron sections which were then riveted together. And at the time, there were no particularly good methods for making sheet metal, so the plates had to be beaten, basically hammered by hand, for many, many days until they were put into the correct shape. In 1839, there was the first ocean-going iron-hulled warship. That was the HMS Nemesis. This was also the first warship to use watertight bulkheads. Bulkheads are basically separating walls between sections of the ship, so that if the ship gets a hole in one part of it, only that particular sector gets flooded, and the bulkheads protect the other sectors of the ship from getting flooded as well. It was 56 meters in length and 8.8 meters in width, so fairly large for a warship. It was fitted with a 120 horsepower steam engine, which drove two paddle wheels, as can be seen here. Armament consisted of two 32-pounder pivot guns and four additional 6-pounder broadside guns. And this particular ship, it wasn't yet armored, so it used iron as the material for the hull, but it was very thin iron. So it wasn't intended to take a explosive shell, or it wasn't intended to take the impact of a solid projectile either, but it was just the first example of using iron as your primary hull material for a warship. And this particular ship was used to great effect in China during the Opium Wars, where the Chinese called it the devil ship, because it couldn't be set on fire because it's iron, it couldn't really be rammed, so all of the ships that it encountered from the Chinese Navy had a very, very difficult time dealing with it. Finally, in 1855, we do get the first ships which were protected by iron armor. These were the Devastation and Etna-class ironclad floating batteries. The Devastation was built in France, Aetna was built in Britain. Both of these were built essentially as a joint international project after the Russian attack on Sinop in 1853. So the designs were basically exactly the same, just with minor differences for like the specific types of guns that were used, and so on and so forth. These were the first warships that were in fact definitely armored. So we know of a couple of ships from earlier centuries which were described as having some iron armor on themselves as well, but that documentation is somewhat lacking. So these are the first ones which are in fact documented, and very well indeed. The ships were built as a wooden hull covered with 90 to 110 millimeters of wrought iron plate and an additional 510 millimeters of oak. So the oak backed the iron plate so that when the iron plate was hit, the oak absorbed most of the energy, but the iron plate made sure that the oak would not be either penetrated or set on fire. The upper deck was not armored with iron, but it was protected by 230 millimeters of oak. These ones were initially developed for around 30 guns, but they never got their full armament loaded onto them. So typically the British Etna class would carry around 14 guns of the 68-pounder range, and the French Devastation class would carry 16 50-pounder guns. The ships are powered by a 150 horsepower steam engine and a 1.8 meter diameter screw for local maneuvering. So once you get it into position, they would be able to maneuver at 5 knots. But if they were traveling on long distance voyages, then they had to be towed into battle. So when these ships traveled from Britain and France, they were towed by significantly larger warships, and they were essentially just taken there, put into a position next to the beach, and then used to bombard shore positions. Because a regular wooden-sided ship, it would try to bombard shore positions, but then it would have to leave after it takes a certain amount of damage, whereas the armor on these guys was impervious to everything that was available to the enemy during the Crimean War. So they were able to just stay in front of the shoreline and keep on bombarding and bombarding until they ran out of ammunition. In 1859, the first actual ocean-worthy ironclad was built, the French Gloire, developed by Henri de Puy-de-Dôme. I hope I pronounced that correctly. This was an example, and the first example, of a broadside ironclad. This means that its ammunition, or its armament, was along the broadside, just like with earlier ships of the line and frigates. Because it only had one deck, it's also called an armored frigate, because frigates by definition were warships with only one deck. And another name is ironclad ship of the line, because even though it had one deck, it was roughly the same length and displacement as a ship of the line. So this particular type of class of ironclads has a whole bunch of names, but they all mean the exact same thing. And the reason that while it was as large as a ship of the line, they could only use a single gun deck is that the iron armor was significantly heavier than wooden armor. So you had to drop down your ship and make it lower in the water so it wouldn't capsize. And also, if you had a second deck of guns, that extra weight was unacceptable. So you improved your protection, but brought down the weapons carried on board. This particular one was armed with 36 and 164 millimeter naval rifles. So that would have made it basically the most powerful ship afloat in the world at the time that it was launched. Armor was 120 millimeter iron plates backed by 43 centimeters of timber. They kept timber backing for the ironclads for the first couple of years, because it was shown that if you have thick iron backed by thick timber, it takes shots better and doesn't fracture over a bunch of shots as quickly as just iron by itself. Also, because the riveting job between iron plates wasn't particularly good, you wanted to have that extra protection behind your iron as well. In this particular case, the armor that was developed for the Gloire was tested at basically point-blank range, 20 meters against 68-pounder rifles, and it held perfectly well. So there was no reason to go for thicker armor than this at the time either. This thing was 78 meters long and 17 meters in beam, displacement 5620 tons. So it's actually a little bit larger than the largest ships of the line that we saw in the earlier lectures, but it carried, once again, just a single deck of guns. And power was provided by significantly larger power plants, so 2,500 horsepower or 1,900 kilowatts, and it gave it a speed of around 13 knots, which also made it relatively fast for its day as well. Then the following year, the British won up the Gloire with the Warrior, which then became the most powerful warship afloat. So the Gloire got to be most powerful just for a single year. The Warrior was the first all-iron-hulled ocean-going frigate. So the Gloire was built with a wooden body, but then iron armor on top of that. The Warrior was just built with an iron hull, just an iron hull directly, and no wooden hull components that were particularly important at all. It was, because it was built with just iron and not a backing wood layer, it was not actually intended to go into battle as a conventional ship of the line, because while the Gloire, with its thick timber backing, it could sit and basically take shot after shot after shot. The Warrior was more protected against individual shots, but not against gigantic volleys of gunfire. So what it was intended to do was to be a fast, independent operational ship that could come up to an enemy fleet, unload some shots into them, and then steam away. So more a little bit closer to the concept of a cruiser in operations rather than a ship of the line. This guy was significantly longer, 128 meters, so the Gloire was 78, this guy's 128, almost twice the length of the Gloire. Beam 18 meters, so relatively similar. Displacement almost twice as well, so 9,000 tons. Power was provided by 5,200 horsepower, and speed was similar at 14 knots. Armor was just 14 millimeters of iron, and it was armed with 110 pounder Armstrong rifled breech loaders. We'll get to those in a few slides. And 26 68 pounder smoothbore muzzle loading cannons. So the breech loaders would have been up on the top because they were more powerful, and some of them would have been on pivoting mounts so that you could rotate which direction they're firing, whereas the 68 pounders would have been just along the deck and been used as on a conventional ship of the line or frigate. And now we get to the evolution of the gun turret. So having a gun that you can rotate and train at some particular target is very useful, because if you can train it, that means you don't need to turn the entire ship in order to fire at that particular target. Swivel guns have been used on ships since the 1400s. This is an early example. These were very light, so essentially this entire gun would only be maybe a meter in length, and they would fire fairly small ammunition, maybe like 2 centimeter thick balls. So this was a hand weapon, but mounted on a swivel. Pivot guns, as you might imagine, were put on a pivoting mount, and these were developed by 1800. They were very popular on privateer ships, especially with the American privateer navy during the War of 1812. So the examples that are portrayed here would be exemplary from American privateers from the War of 1812. And one famous example is Otway Burns' ship, the Snapdragon. In this case, what you had was a metal track ring, which was usually somewhere between like 3.5 to 4 meters in diameter. That track ring would be shaped as a U, and you would have a carriage that had small wheels that was constrained within that U. So you were able to rotate the gun around the center without having to worry that the gun might like slide left or right or backwards or forwards. The gun itself was put onto a conventional carriage. It's just that conventional carriage was then married to this H-shaped member, and the way that you would rotate one of these guns is you would have a handspike, or essentially a crowbar, that you would shove under one of the edges, and then you would force it to rotate. So that way the wheels were essentially stuck in between the metal of the ring, so that way once you rotated into position, it didn't just start randomly rotating in some other direction, which was very, very important, because out at sea you'll almost never have flat, calm water. You're always having the ship rocking back and forth. So you want to make sure that you can rotate the gun, but also keep it constrained in that specific direction in which you want it to be facing. In 1820, the U.S. built the schooner USS Alligator. This was the first full-size ocean-going warship that was also armed with a pivot gun, and this one was also the first warship that was armed with a mount that was set fairly high. So in this case, you can see that the gun is extended above the highest level of essentially the deck wall. Usually what you would see on some of the earlier guns was they were much lighter, so they were mounted on elevating carriages, whereas this one was just mounted on a permanent carriage that was set relatively high. So that way you had extra range of fire and you did not need to worry about like accidentally hitting your own ship while you're using it. Also, the mount did have one disadvantage, which is because it was completely open, it was vulnerable to enemy gunfire. So if an enemy fired a shell and it hit, for instance, your mast, then splinters from the mast could damage and injure the crew, or the mast falling down could destroy the gun. So this was not a perfect solution if you wanted to just rotate the gun in some random direction and fire at an enemy that is anywhere in your general vicinity. So the next step in the evolution of the turret, we had the armored gun cupola. This was designed by a British naval engineer called Cowper Phillips Coles in 1855 during the Crimean War as well. In this case, he essentially had just a raft, which was called the Lady Nancy, and it was used to shell shore positions during the Crimean War. So in this case, what he did was he had a gun on a pivot mount, and that pivot mount was then protected from above by an armored cupola. And the armored cupola was oversized so that the gun could be wheeled in and out on its pivoting carriage. It also had several ports, so you could either fire out the front or out the sides. But the cupola itself was stationary, so this was not yet a true turret. This was just a protective encasement for a gun, but it was the predecessor of a turret. And in fact, from experiences developing this, Cowper Coles went on and developed the first actual turret. This one was mounted in 1861 on the HMS Trustee. The Trustee was one of the original Etna-class ironclad floating batteries that he also was involved in developing. And what he did was he used a connection, essentially a shaft that was connected to the steam engine, so that the engine that drove the ship could also be used to turn the turret around. Because this turret already weighed over 20 tons, so you could not possibly use just pure manpower to turn it. So in this case, he had the steam engine you could basically connected to the turret, so that if you needed to rotate the turret, you would just engage a particular gear, and when you engage that particular gear, the turret turns either to the left or to the right, depending on what you need to do. Also, this was, so because of that, this was the first comprehensively armed turret gun house. Gun house is a term that is used because it's sort of like a little house that houses some guns on the inside. As many other turrets on warships did in subsequent decades, this particular one had 2 guns in it, and the turret itself was developed so that the sides were sloped and the turret itself was conical. The reason for this is that if you slope your armor, it has a greater effective thickness along the horizontal, so it would allow you to use a thinner metal but have greater protection for the gun and for the guns and for the crew that are inside. There were a few motivations for gun turret development. First one is that because iron armor added a lot of weight to warships, you needed to balance the weight by decreasing the number of guns. But if you decrease the number of guns and you can no longer use a large broadside, then you don't really want to have just like 2 guns sticking out one side, 2 guns sticking out the other side, and you have to turn your entire ship just to use those 2 guns. So a turret allowed you to train those few guns in any direction without having to worry about the entire ship, which would then make the ship itself more maneuverable, because now you can swim in any direction and fire in any other direction. Also, it makes the ship more responsive because it's a lot easier to turn a 20-ton turret than a 5,000-ton ship. It's going to be able to rotate the turret a lot faster than it can do a tight turn, and therefore also you don't need to worry about accidentally like ramming into another ship that might be in the way in case you're trying to get your guns trained on some particular target. The guns and ammunition improved in effectiveness over the past couple of centuries, and particularly over the preceding couple of decades. So the gun caliber increased and the length increased as well. It allowed you to use heavier ammunition, so you didn't need as many guns to cause as much damage. You had longer range because a longer barrel gives you more speed, and more speed on your shell gives you a longer range of fire. And it gave you better accuracy because now you were able to machine guns which were more accurately milled or bored, and so on and so forth. Now, also explosive shells were available as ammunition, and they were far more destructive than solid shot. So once again, you did not need the entire battery of 100 guns facing out the 2 sides. You just needed 2 or 4 to do the exact same amount of damage. And this is a particular example from the Dutch ship, Torpedo or Torpedo. So this is a turret that they had on this particular monitor. It had 2 heavy guns on the inside, and the vast amount of space that was inside the turret would have been used to store ammunition, store random supplies, gunpowder, and so on and so forth. So one disadvantage that this created then was that these original turrets were very, very heavy, because essentially all of the structure that you wanted to have controlling the turret was immediately below it, so it was essentially part of the turret. The engine, or all of the gearing and all of the shafts that went out to the engine, they had to be very heavy and sturdy in order to be able to turn this very heavy construction. And because it was loaded inside with ammunition and so on and so forth, that made the turret even heavier. So one of the problems that this created, and we'll go into this in a little bit more detail, is that these early turrets were super heavy, so they have to be set fairly low in the water. Otherwise, if you have a very heavy object set very high up, your ship can capsize very easily, and you generally probably don't want to have that happen. A couple of additional developments within artillery in general. We have the development of the first practical mass-produced rifle breech loader. This was the 1855 Armstrong gun developed by William Armstrong. The most important piece of innovation that went into this design was the Armstrong screw breech. The issue with earlier designs for guns that were breech loaded was that it was very difficult to seal the gases from the explosion. So if you load your gun from the muzzle, then the back is already sealed by default, so the gases don't have anywhere to go. But if you are trying to load from the back, which was the easier way to load, then you need to make sure that your back, your breech, is sealed against those high pressure gases, and that has proven to be very difficult. So this was the first solution that was actually fairly widely used for a few years. In this case, what he had with the Armstrong screw breech was there was a vent piece, which is right here, which was slid behind the powder chamber. This is the powder chamber. And then once you slide this piece, you have a screw which essentially presses forward into it and presses it against the powder chamber. So you have a metal on metal fit, and it was not perfect. There were still some explosive gases that were able to escape, and it didn't give you a perfect seal, but it was effective enough to be accepted for service and be usable significantly better than most other earlier breech-loaded variants. Also, this was the first modern built-up gun. So earlier, when we looked at guns, the way that you made a gun was you either cast it in a single piece, or you cast it and then bored it out, or you cast it with a core. This one was the first real modern type of gun. So in this case, you have several cylinders which you fit over each other. So what you would start with is you'd have an inner tube, which was very commonly called a tube, at least in British terminology. And this is also called the liner, because it essentially lines the inside of the gun. And this particular one, you would want to be initially under compression. And then over and around this liner tube, you would want to have a jacket of a bunch of other tubes, which are themselves under tension. So the reason for this is that if you just have a regular homogeneous gun, then the thickness that you can make for the metal that would be around the breech area, the effectiveness saturates around like 50% of the caliber, because if you have something much, much thicker, then you just have issues with crack propagation. With, let's say, you fire 50 rounds, you have some cracks initiating here, and then you essentially lose all of that extra thickness. So what was realized is that if you want to make sure that your gun is able to take a larger force of explosion without blowing up and killing everybody who's trying to man the gun, is if you have a liner which you initially compress to the elastic limit, which during firing expands to the expansion elastic limit. So the way that you would do this is you would start out with a liner, and once you have the liner in place and is manufactured, you take your initial jackets, such as in this case 2B, 1B, the B2, and so on and so forth, and you would heat these up. And when you heat them up, you initially prefabricate them so that they're smaller than the outer diameter of the liner, but as you heat them up, they expand. And when they've expanded, you slide them over the liner, and as they cool down, they compress the liner. And if you do the development correctly, then ideally you'd be able to compress it to the elastic limit. And once you do that, then if you need more strength, then you take your following pieces and you heat them up, you slide them over the inner jacket, and you wait for them to cool down so that they compress the inner jacket and compress the liner even more. And you do that continuously until you've built up enough layers that your gun is going to be able to survive the force of explosion. So sometimes the thickness of the gun would be relatively reasonable. Other times, like on this one, the thickness of the metal grew to tremendous proportions. So in this particular case, you can see the liner is essentially that inner tube, but it's covered by jackets which take it almost to twice the diameter. So depending on how much force you were expecting to apply and how good the quality of your metal was, you might need either more or fewer jackets. Also, the jacket usually would taper towards the muzzle because you really only need your largest amount of thickness at the breech. So if you taper it towards the muzzle, then you can save weight because there isn't just that much force applied on the jacket here. Also, what you would occasionally find is that as you use the gun, the liner is eroded with every single shot because the hot propellant gases, they melt a little bit of the metal from the liner and it's basically blown out of the gun. So with every single round, the caliber of the gun would increase by a very, very small margin. And eventually it would increase to the point that your shell is no longer able to seal the gun, and then you just have all of the explosive gases just escaping past the shell. So what you would do in that case is you would drill and bore out the liner on the inside, and you would reheat the rest of the structure and insert a fresh liner from the front. Or at other times, if your liner was conical, so it would be thicker at the front and thinner at the back, then what you could do is you could heat up the front structure while cooling the liner and then just pull it out and insert a fresh liner in that way. So this allowed you to save significant amount of money because if an earlier gun was at the point that you were fearful of it breaking down, then you'd have to melt the entire gun. But in this case, you just have to melt down the liner and the rest of the material you can reuse for the next version of the gun. Also, the Armstrong gun had additional developments in ammunition. These were developed from the 1846 Wertenhof Cavalli system that was developed in Sweden. And in this case, what he used was he used pointed shells that were made from cast iron, and they were applied a thin lead coating. The thin lead coating was to provide a soft metal which could be deformed by the rifling, so that the shell would have rifling grooves automatically cut into it, and it would spin, and therefore you don't need to worry about making your shell out of some convoluted structure which would be very difficult to manufacture. Rifling on the Armstrong gun was with several grooves, and usually at one full turn per 38 calibers of length. And the gun was also developed with a squeeze bore, so that means that the barrel was slightly smaller at the muzzle and slightly larger at the breech. Though what this would do is essentially it would center the round before it leaves the barrel, so it gave you better accuracy. And also, as the round went through the slightly thinner barrel, it smoothed out the lead coating, so it gave the round more aerodynamic properties, so it could fly a little bit farther as well. The Armstrong gun was accepted for service in 1859, but then production stopped in 1864 because the design of the gun and the ammunition for it was significantly more expensive than the muzzle-loading guns that were in use at the time. And even though it was significantly safer to use because of the built-up construction, it was more complicated, and it took more time to just load and get it operational. So therefore, the British Navy and the British Army decided that they don't really want to pursue the concept after field testing it for a few years. Also, you have the development of a new muzzle-loading gun called the Dahlgren gun in 1855. The Dahlgren gun, you can think of it as an improvement on two earlier types of guns: the 1824 Poison gun, which we already saw, and the 1811 Columbiad. The Poison gun was, once again, the naval gun developed to fire explosive shells, but the way that Poison developed it was that it was only able to fire explosive shells, because it was made out of material that was too thin to take the full brunt of a solid shot. So therefore you could not use solid shot, because when you use a solid projectile, if you want to have it fly to the same distance, you need to use more gunpowder. That creates higher internal pressures, and therefore the gun needs to be physically stronger in the breech and around the gunpowder chamber. And the Columbiad was a gun that was originally developed for coast protection, which was able to fire both solid shot and shells on high or flat trajectories. but it was significantly heavier, and therefore it was useful for seacoast duty, but not so much for mounting onto a ship. And the development of the Dahlgren gun specifically was inspired by the 1844 tragedy on the USS Princeton, when a new, very heavy Poison gun was being tested with ammunition, with live ammunition, and it was being demonstrated to a lot of government workers, and including the president of the US at the time as well. And it exploded, and shrapnel killed a few people, including, I believe, a few national secretaries, and almost killed the president as well. So after that, Dahlgren decided that he needs to develop a safer gun. So the way that he approached the problem was to make a gun that was developed more scientifically. And his guns are called the soda bottles, because they sort of look like soda bottles. This was to make sure that there's no particular discontinuities where stress can build up, and therefore the gun would be able to take the stress of each shot significantly better. The guns were developed also using more scientific design and experimentation, so before starting to cast it, he went through quite a few years of developing and testing, and then seeing what kinds of shapes might tense, what kinds of shapes were most resilient to explosion and failure, and so on and so forth. And once again, obviously, he used the thickest metal around the powder chamber, and then thinned down the barrel as he went towards the muzzle to minimize the weight. And an important sort of remark is that not a single Dahlgren gun blew up in service during the Civil War. So most of the other guns had at least a couple of failures, but not a single Dahlgren design gun failed. This is Dahlgren himself, John Adolphus Bernard Dahlgren. He was himself a Navy officer. The Dahlgren gun, because of its design, it was able to use the full range of available ammunition. It could fire solid shots, explosive shells, canister shot, grape shot, and shrapnel. The difference between the last three is that a canister shot has effectively a bucket full of various shrapnel, whereas grape shot and shrapnel, you fire the materials out directly without a bucket. So it's sort of like shooting a shotgun with a shotgun shell, or just loading it with a bunch of shrapnel directly. Dahlgren's gun was built traditionally, so it was cast in a solid piece, and then the bore was drilled out, as we saw was developed by John Wilkinson back a couple of lectures ago. And it was satisfactory up to 13 inches of caliber, but beyond that, it was too brittle as well, because if you cast a gun solid, it is stronger than if you cast it with a core, but it still cools from the outside to the inside. So it shrinks the outer layers first, and then the layers below them begin shrinking, but as they shrink, they essentially begin peeling away from the layers on the outside, so you have the entire material in tension, and therefore it sort of already wants to blow up on itself. So something better was required if you wanted to make even a Dahlgren gun to be of larger caliber than 13 inches. And elevation for these was typically a corkscrew, so this would allow you to aim the gun up and down relatively accurately, and pretty much with to any angle that you might be interested in. The next step up from Dahlgren's design, especially important for improving larger caliber guns, that's a 20-inch example right there, was the Rodman gun. And what Rodman did was he took the Dahlgren design but made the casting process more scientific. So the cannon was cast in a two-part with a two-part core. The core had an outer section and an inner section. The outer section was essentially part of the mold, and it was closed at the bottom. And the inner section was just a hollow pipe, which he would use to flow water. So the way that he would cast this gun is he would pour the liquid metal into the mold, and then he would push cold water through the inner core tube, and then as it got pushed down, it filled up the tube, and because pressure was applied, it then got pushed out. So he continuously had cold water going through the core, and while the cold water was going through the core, there was a fire that kept the outer mold hot, so that this gun cooled from the inside out. It was significantly more expensive to make guns this way, because you had to provide all the water and the corresponding fire to keep it hot on the outside and cold on the inside, but it made guns significantly stronger and more reliable. So, for instance, for an 8-inch Rodman gun, you would need a total of 65 hours of cooling and about 190 tons of water going through the core, but it was worth it because then the gun was significantly stronger, because it cooled from because it cooled from the inside out, the layers were in complete compression, and because they were in complete compression, then the material was more resilient to fracture. And after he would finish molding the gun, then it was just machined, so it would be bored out to the size that you actually want. The exterior would be turned, and you would turn the trunnions, which are the little things that hold the gun on a mount. A few developments in firearms around the same time as well. We have Colonel D. Davidson, who developed the world's first optical sight in 1850. This was the first scope for long-range rifle fire, and it was developed for the pattern 1853 Enfield rifled musket for the Crimean War. The reason that earlier firearms didn't really need optical sights is because they were far too inaccurate. You couldn't really hit anything reliably out to just 100, 200 meters. But this gun was already able to take relatively accurate fire out to a distance of like half a kilometer or even closer to a kilometer. So therefore, you now had the reason and the motivation to improve the accuracy of your rifle fire. In 1857, we have Sir Joseph Whitworth developing the Whitworth rifle. This was the first rifle that was accurate enough to be considered a sniper rifle. The way that he made it accurate is that instead of doing a round barrel with rifling cut into it, he made the profile of the barrel hexagonal and turned the hexagonal shape to make the rifling down the barrel. And because of that, the bullets themselves were also hexagonal, so that they fit perfectly with a hexagonal barrel. It made the gun significantly more expensive to manufacture, but also made it extremely accurate. So while the Enfield could get you accurate fire onto a human-sized target to maybe like 1.2 kilometers, this one gave you accurate fire out to 1.8 kilometers. And because it was more expensive, because of this complicated production method and the complicated bullets, it was 4 times more expensive than the 1853 Enfield. The British Army did not want to use it. Also, it was more prone to barrel jams because the hexagonal shape would build up a lot of residue over time, and if it was not properly cleaned out, then a bullet could just get stuck in the residue and the gun would burst. However, it was offered for sale internationally, and most famously it was sold in the US Civil War to the Confederates, where it was used with Southern sharpshooters, and it is responsible for the highest ranking kill that the South had. I forget the exact name of the general, but there was a Union general who tried to motivate his men to go into an attack, and he died with the last words saying that they could not hit an elephant at this distance. And right after he said those words, he was standing full size up, and he was hit directly in the head and fell down and died. And that was because of one of these guns. In 1848, we have the first step on going in the direction of developing the repeating rifle. This was Walter Hunt's rocket ball. It was the first caseless metallic cartridge. The way that he developed it was he took the mini ball, which we saw developed earlier, and also used a hollow space in the back so that the bullet could expand, seal the gun or seal the barrel and engage the rifling. But this hollow space, instead of just being left hollow, it was what was filled with gunpowder. And on the back, it was sealed with a wooden cap. The wooden cap had a little hole in the center, so you could put an essential percussion cap. And in 1848, along with the bullet, he developed his volition rifle, which was the first lever-action repeating rifle, which means that you had a lever which you could turn up and down, and that lever action would then automatically reload the next bullet into the chamber. So instead of having to manually load each individual bullet, you could load all 12 into this tubular magazine, and then every single time that you pulled on the lever, it would automatically load the next round. You could fire, load the next round, you could fire. So firing rate could be significantly higher with this particular type of gun than with earlier types of muskets. So in 1849, Lewis Jennings took the design of the Hunt volition rifle and slightly improved it, and came up with the Jennings rifle. And both of these ended up being bought by Winchester. So the Winchester repeating rifle was basically the grandson of the Hunt rifle and the Jennings rifle. So you can basically say that these are the grandfathers of the gun that won the West. And then in 1860 we have the Henry rifle, which was the first relatively mass-produced repeating rifle. Benjamin Tyler Henry developed his gun independently of the other two, but obviously he used similar concepts. He improved on the design, but also added quite a few improvements of his own. And it ended up being the first mass-produced repeating rifle, but it was really only offered for sale to individuals because no army wanted to accept it for official service. The rifle design was that it was a lever-action breech loader for 16 rounds. The rounds, once again, were held in the tubular chamber beneath the barrel. On the downstroke, the old cartridge was ejected, and the hammer was automatically cocked. And then on the upstroke, the new cartridge was pushed back up and into the chamber, and then it was ready for firing. And then the way that this gun was described by the South, because most of these were bought by the North, was that this was the gun that you could load on Sunday and fire all week, because it just had so many rounds that you could load into it. The round design in this case was a copper or brass rimfire cartridge. So rimfire, as we had described at the last lecture, uses a percussion cap, which is the entire rim. So you don't need quite as much precision on the needle that hits the percussion cap. The bullet itself was 14 grams of lead, and then it used 1.6 grams of gunpowder to fire the bullet. There was also the Spencer rifle, also developed in 1860, and this was the first rifle that was actually accepted for military service by the U.S. Army. And in this case, you had the rounds inside of the stock rather than inside of a barrel or inside of a tube beneath the barrel. It had significantly smaller amount of rounds because there was only seven rounds that you could fit into the stock instead of the 16 you could fit beneath the barrel, and this also used a copper rimfire cartridge. Also, a difference from the Henry rifle is that with the Spencer rifle, you had to cock the cock manually between every single shot, whereas with the Henry rifle, on the downstroke, it cocked the hammer for you, so you did not need to have that extra step done by hand. And in 1861, we have the Gatling gun being developed by Richard Gatling. This was the first widely used true rapid-fire firearm. So in this case, what he had was a hand crank mechanism with 6 rotating barrels. Later designs had up to 10 rotating barrels. Each barrel was provided its own firing pin and lock in the back. And what ended up happening was there was a central cam that was non-symmetric, and as the barrels were rotated against the central cam, it either pulled back and locked the lock, or it released and fired the pin into the round that happened to be in that particular barrel. The cartridges were held in either a case or just a hopper that you could dump a bunch more rounds into. They were lowered into the gun individually down this chute, and initially the forward motion of the lock as it was pushed by the cam would load the cartridge into the barrel, and then at the highest point it would release the firing pin, and the firing pin would engage the round would leave, and once the lock was taken back after it left the cam, it would expel the cartridge back out. This was developed for initially steel cartridges that were developed by Gatling himself, but he realized that they're not going to be mass produced, so he adapted the design to use paper cartridges for the first mass produced Gatling guns. And finally, once brass cartridges became more widely available as ammunition, he once again adapted the design to use brass cartridges, because obviously a paper cartridge would be at greater risk of getting either crumpled up or jammed and cause a jam in the gun. So once brass became widely available as your cartridge material, it was the material of choice to use. And with the Gatling gun, you had relatively high rate of fire, or absolutely high rate of fire for its time, 200 rounds a minute. It is still technically fairly respectable, even for modern machine guns. But most of the time, you would not use it quite at maximum range because the person couldn't really keep on cranking the crank at full speed. So most of the time, it would be used closer to maybe 60 rounds a minute, which is still pretty darn good, considering that everybody else only has a few rounds a minute from their firearms. And also we have some developments in naval mines. This is Morris Herman's von Jacobi's mine from 1851, the first combat-worthy naval mine developed in modern times. It was essentially a wooden cask that was filled with gunpowder. It was 0.7 meters tall and half a meter in diameter, and it had 10 to 14 kilograms of gunpowder depending on the specific design. From the bottom, it was anchored to the seabed so that it was floating in the water at some particular height and at a specific position. It was connected to a shore-based electric power source, and it had an iron shaft protruding upwards out of the barrel. If a ship hit the iron shaft and pushed it down or deformed it, it would close an electric circuit that was up here. Once the electric circuit was closed, it would send a short circuit and blow up the gunpowder. So the reason that you had an electric circuit is that if you wanted to go out and maybe take out the mines or replace some of them, you could just turn off the electric power from the shore, and then all of a sudden this mine is no longer functional. So this was a way to make sure that you could have it be deadly to your enemy, but not deadly to yourself. And also, right around the same time, you have Emmanuel Nobel's naval mine in 1852. This was independent of an external circuit, so it could not be made essentially safe, but it was also somewhat cheaper because of that. And this was also essentially a wooden cask. In this case, it was tapered, loaded with significantly less, so just 3 to 4 kilograms of gunpowder in the bottom. The detonator was a vial of sulfuric acid that was up at the top, and if the mine was hit, there were several spring-loaded metal rods that were very, very sensitive. So if it was disturbed by physical impact from a ship, then one of the rods would snap, it would break the sulfuric acid vial, the sulfuric acid would mix with another chemical to produce a chemical detonation, and that would trigger the detonation of the gunpowder. So these were technically cheaper, but they were also found to be less reliable than Jacobi mines, so they were not quite as popular in use. And both of these mines were developed for the Russian Navy, and the Russian Navy was the first one to make use of mines in modern warfare when they used them during the Crimean War. So the Crimean War technically had a lot of innovations, because we went over ironclads, we went over new artillery types, new firearms, and even naval mines. The first successful use of combat mines was in June 9th, 1855, when 2 British paddle frigates, the Merlin and the Firefly, hit Russian mines protecting the city of Kronstadt. And with this particular incident, the Merlin ended up hitting one mine. As it tried to get away from the minefield, it hit a second mine. The Firefly decided to come help, and it hit a mine as well. So both of them ended up making it safely back out of the minefield, but there were a lot of surface damages, and they needed to go into fairly significant repairs. And then on June 20th, the Vulcan hit a mine as well, and right after that, on the same day, the British Army decided that they want to get rid of mines that are protecting Kronstadt, so they undertook the first minesweeping operation. And in this case, they just had a bunch of rowboats towing ropes with hooks on them, and the hooks would be used to then catch onto the anchors beneath the mine, and then the hooks were also sharp so that they could cut the anchor and they could just lift the mine out of the water and then either use it for study or just dispose of it. And they were able to recover 33 of these infernal machines, as they called them at the time. And we get to the US Civil War. Incidentally, one of the most technological wars of the 1800s. It had the first fairly widespread use of observation balloons, especially early on in the war. It had the first widespread use of armored trains and the first use of railway artillery of relatively heavy caliber. The first use of ironclads in actual combat, the first widespread use of the mini-ball. So the mini-ball, as we discussed earlier, was the first conical rifle ammunition that had significantly longer range than just little ball-shaped ammunition. And because it had longer range, it was, first of all, more accurate. It had longer range. It was itself heavier, so it caused bigger and stronger wounds. And the thing that a lot of generals of the Civil War didn't realize is just how much more effective it was. So they were used to older types of ammunition, which you could shoot 100, maybe 10 of them would hit somebody in the enemy army, so you could launch an entire frontal attack against a column of soldiers with rifles. But with the mini-ball, by the time that column made it to that position they were trying to attack, most everybody had already been hit because they were a lot more effective. So because of that, the mini-ball is believed to have been responsible for 90% of all battlefield casualties from the Civil War, as compared to just 9% of casualties caused by artillery fire. And out of those people who were wounded by mini-balls, 15% of the wounds were lethal. Also, because the ball was a lot heavier and fired with a greater muzzle velocity, its impact was stronger, so a lot of bones were broken just on impact, whereas an earlier ball that was actually spherical and significantly lower in speed would just give you a flesh wound, but it would not actually blow your entire arm off. Also, the first use of rapid-fire firearms, such as the repeating rifles that we mentioned, and the Gatling gun. So, naval developments, we have some evolution of ironclads. The first ironclad built in the Civil War was the Southern CSS Manassas. This was the first ironclad built by the Confederates, and what they did was they basically just took a commercial ship covered it in iron, and made it into an ironclad ram. Most of the ship's body was underwater, and only a little bit was sticking above water. This made the ship significantly more protected because a cannonball that goes through the water before hitting you basically loses all of its potency. And because of the significant slope on the armor, they didn't really need to use that much of a thick iron in order to have it be very effective against cannonballs as well, because they would just bounce off of the turtle-like body. In fact, it was protected just only by 32 millimeters of iron plating, except pretty much every single northern ship that it met in combat found that all of their cannonballs, no matter how heavy, they just bounced right off the top. The weapon that it carried was obviously the ram in the front, and also a 64-pounder Dahlgren gun right in the front as well. And once again, most of the ship was submerged. And this was the first ironclad that was used in battle at the Battle of the Head of Passes in October 12, 1861. Although nobody ended up dying at that battle, quite a few shots were fired at the Manassas, and not a single one of them did really much of anything. Then we have the CSS Virginia, or as it is more commonly known as the Merrimack. The reason that it is called the Merrimack was that the Merrimack was a northern ship which was sunk by the Southerners. Then they raised the wreck and used the wreck to build their ironclad. So in Confederate service, it was the Virginia. And this was the first casemate ironclad. So with earlier ironclads, we saw that most of them had their weaponry installed along the side like a frigate, but the sides were themselves relatively flat. With this one, you have the sides themselves sloped so that you make essentially like a little sloping house. And this was, once again, because sloped armor is more effective. And in this particular configuration, that is called a casemate ironclad, because the superstructure is a lot different than you just have with the straight flat sides that you have on armored frigates. The Virginia was actually pretty big for a ship, for an ironclad of that time. It was 84 meters long, almost 16 meters in beam, and displaced 4,000 tons. The armament was two 7-inch Brook rifled muzzleloaders and two 6.5, basically 6.5 inchers. Also 6 9-inch Dahlgren smoothbore muzzleloaders. Those were the ones that were along the side ports here. And also two 12-pounder howitzers just for close range defense against like light boat that might be trying to attack it from close distance. Armor was 4 inches of iron plate backed by 24 inches of oak. So in this case, once again, they used oak to back the iron, because if you use timber to back your iron, and then the iron is able to take more shells before it finally fractures. And this was sloped at 36 degrees from the horizontal, so relatively flat indeed. And performance, it was fitted with a 1,200 horsepower engine, which gave it a speed of 6 knots, so not particularly fast, but it's good enough for river operations, which is the only type of operations that it was really involved in. So the Virginia, or the Merrimack, was the most famous ironclad of the South. The next ironclad is obviously its northern compatriot, the Monitor. The Monitor was in fact the first warship designed from the start to carry a gun turret, developed in 1862 by John Erickson. And this guy was significantly smaller, so it was only, only 54 meters long, and 12 meters beam and displacement of just 1,000 tons, so basically 1/4 of the weight of the Virginia. It was built with a very low freeboard. Freeboard is basically the height to which the ship extends above the water, wherein during heavy water, in fact, the surface would be almost submerged in the water directly. And the reason that it was built with a low freeboard is, once again, so that you have less of your surface exposed to enemy gunfire, and therefore your ship is protected against incoming shells. The armament was just 2 guns, 11-inch Dahlgren smoothbores in the central turret. The turret was protected with 8 inches of armor, the waterline belt was protected with 5 inches of armor, and the deck was protected with 1 inch. Because normally the shells that would be coming in on horizontal trajectories, so if it comes in on a very horizontal trajectories, even 1 inch at that angle is very, very high, so they just bounce right off. Performance was basically the same as with the Virginia, 320 horsepower and then 6 knots per speed. And this particular ship gave its name to the entire class of ships called the Monitors, where the Monitors are ships that are relatively small with a vastly oversized turret. So if you see a modern battleship, a battleship has a much, much smaller turret compared to the size of the rest of its body. And in here, you can see the gears, the gear train that would turn the turret when you needed to train it at a different target, and then it would be connected to the steam engine that was down below deck. The first battle between ironclads was in fact between the Monitor and the Virginia, or the Monitor and the Merrimack, the Battle of Hampton Roads in 1862. In this case, neither ironclad could really penetrate each other's armor, although one of the reasons that has been suggested is that the Virginia was only provided low amounts of gunpowder, so they couldn't use a full gunpowder charge to avoid running out of gunpowder in one go, and the Monitor had issues with its guns on that particular week, so it was also not using them to full capacity. But essentially they swam, so the Battle of Hampton Roads began when on the preceding day the Virginia steamed in and destroyed 2 northern wooden ships, and then the Monitor came in to face it, and they shot at each other for the entire day, and literally nothing happened to each other, so they just went their own ways and went home. And this battle sent a message to pretty much the entire world that, oh my gosh, an ironclad can destroy 2 wooden ships within a space of a few hours, but it cannot destroy another ironclad, so we have to start building ironclads. So this battle was a really big motivator for more nations to start mass producing ironclads of their own. You also have the development during the Civil War of multiple turret monitors. This is the USS Keokuk, not really a monitor because these towers were stationary and didn't rotate. It's just that the guns were able to rotate internally. But it has the concept that you have 2 positions from which you can fire in several directions. In this case, the turrets had positions on the left, on the right, and in the front or in the back. So each gun had 3 positions from which it could fire, and it was set on a pivoting mount in the center. And in this case, it was also, once again, armored by a layered slab of iron and pine. The first true multiple turret monitor was the USS Onondaga in 1863. This was the first multiple turret monitor to be commissioned. It was somewhat larger than the original monitor, at 69 meters in length, 15 meters in beam, and displacement 2,600 tons. It was armed with 2 15-inch Dahlgren smoothbore muzzleloaders and 2 150-pounder parrot guns, which were rifle muzzleloaders. So one of the reasons for this is that the Navy wanted to compare how effective is a smoothbore versus a rifle gun. So if you mount 2 on both of the types on the exact same ship, then the people who are manning that ship can tell you exactly which one is more effective because they see them in action. The armor in this case was thicker, so 12 inches of armor on the turrets, a 5.5-inch armor belt, and once again 1-inch armor on the deck. The first multiple turret ironclad to actually though be launched was the Minamoto class USS Agamenticus. I have no idea where they got these names. And this one was launched just a couple of months prior to the Onondaga. It was somewhat larger, so 79 meters long rather than 69, 16 meters in width, and then displacement of 3,400 tons. And in this case, all 4 guns that were inside these 2 turrets were the smoothbore Dahlgrens. And in this case, armor was a little bit thinner, so 10-inch on the turrets and 5 inches on the belt, and 1.5 inches on the deck. And then finally, in 1855, you have the USS Roanoke, the first triple turret monitor. But it was found to be very unsuccessful because it was too heavy for its size. It rolled very badly in heavy seas, and just manning it proved to be a very unpleasant experience for everybody who was manning it. But it was 80 meters long, 60 meters in width, and in this case, each of the turrets had its own pair of guns. So one of them had 15-inch Dahlgren smoothbores, one of them had 150-pounder Parrott rifle muzzleloaders, and then the other one had 11-inch Dahlgren smoothbores. The reason that they went with 11 inches instead of 15 inches is to try to cut down on the weight, because they realized that 3 turrets are giving you way too much top loading for something that is actually relatively small in overall dimensions. And once again, armor roughly the same as before, 11 inches on the turrets, 4.5 inches on the belt, 1.5 inch on the deck. During the U.S. Civil War, we have the first ship that was actually sunk by a modern naval mine, and in fact the first ship sunk by a controlled detonation of a naval mine. This was the Union casemate ironclad USS Cairo. Casemate ironclads are associated with the South because the Virginia was a casemate ironclad, but the vast majority of ironclads that were built by both sides were in fact casemate ironclads. Monitors were a relatively small subset during the Civil War. And the USS Sparrow was actually engaged in a mine clearing operation at the time, so the mines that it was clearing out had their detonations controlled from a shore position, so the Confederates on the shore just sent a detonation signal to the mine, and it blew up under the Cairo when they were not expecting it to. You also have the first submarine to sink an enemy ship. This was a Confederate submarine, H.L. Hunley. It was built by the Confederates to try to take out Union ships from underwater, and in fact it did so on February 17, 1864, because when it detonated a spar torpedo against the hull of the USS Housatonic. The spar torpedo was basically just a bomb held at the end of a very, very long pole. So the pole, which you see the base of the pole here, would have basically been as long as the submarine and held out in front and detonated once it hit the bottom of the Housatonic. In this case, however, it proved that the pole proved to be too short because the bomb was quite potent, and the concussion from the detonation went through the submarine and killed the submarine crew instantly. So the submarine was lost with all hands, and it was uncertain what happened to it until just a few years ago when it was discovered at the bottom of the bay. And when they discovered it, they realized that the entire crew was still sitting in their positions, and that motivated a study that led people to realize that a spar torpedo, the size that they used on the Hunley, the detonation shockwave would essentially burst every single blood vessel in your body, including all the blood vessels in your brain. So the entire crew was literally killed by having every single blood vessel in their body blow up during the moment of detonation. Also, this is the most southern way to protect a ship. You clad it in cotton. I absolutely love this concept. Cotton clads were actually used by both the North and the South, but significantly more heavily used by the South. In this case, you had a conventional steamship or like a steamboat, and then you would line the superstructure with just hundreds of bales of cotton. And the cotton was hopefully then soften the impact of incoming shells and then protect the superstructure. So some ships had cotton bales installed just directly on the outside, like you see on this example, and on this example, and also on this guy, which is the CSS Stonewall Jackson. You see cotton protecting the entire superstructure all the way around, whereas other ones had cotton bales that were compressed between layers of pine. So this is an example, the CSS General Sterling Price, which from the outside it just looks like a regular steamboat with wooden walls, but the walls are very, very thick, and they have cotton in between pine to make sure that you can thicken it up, but also have it be somewhat light. So cotton was not very effective at protecting your ships, but I mean, desperate times call for desperate measures. Also gives you a good laugh.
It sort of reminds me of the way a soft body armor made of Kevlar works.
Right.
It's not like conceptually quite that ridiculous, I feel.
Yeah, yeah. It's just that when you look at the concept for the first time, it's like cotton versus shells. Yeah. Oh well. Also, you have the development of the first artillery rail cars. This is the earliest illustration that at least I'm aware of that came from Frank Leslie's illustrated newspaper edition released on May 18, 1861. This shows an armored rail car that is pushed in front of a locomotive. The iron protecting this car is half-inch iron boilerplate, and it was built by Baldwin Works in 14 days between conception and release. The car was 65 feet long, 9 feet wide, had 50 firing ports, so mostly along the sides, but also some out in the front, for rifles for soldiers, and also a 24-pounder gun facing out the front. This particular one was developed to defend some workers who were repairing bridges near Baltimore from the Confederates. And after this, you really start having the development of more and more and more types of railroad artillery, railroad cars, armored trains, and similar machinery. The first combat use of railway-mounted artillery was in June 29, 1862. Robert E. Lee suggested to take a heavy cannon, put it onto a flat car, and armor that flat car. So the vehicle that was produced was nicknamed the Dryland Merrimack because it was sort of like the Merrimack except it was on land. The gun that was used for this particular one was a 32-pounder Brooke rifled muzzleloader. It was put onto a flat car, as can be seen here, and it was given partial armoring. So from the front, it was armored with 4 inches of iron and then 18 inches of wood. and then from the side it was just armored by wood. There are some illustrations that show it being a significantly larger construction, but there doesn't seem to be too much actual historical evidence backing something like that. So most likely it was an actual construction that like this, which were photographed later on in the war as well, where you just have armor protecting it very well from the front, because you're expecting that this gun would be advancing in line with a bunch of soldiers, so hopefully nobody should be attacking it from the sides. The full car was around 60 tons, because it also had additional length for ammunition on board, and it was provided with 200 ammunition rounds. And then towards the back, once again, they used some cotton bales to protect the crew, because it's Robert E. Lee and you're the Confederate Army. And you got a lot of cotton. Also, the North had their own armored trains, which they nicknamed the Railroad Monitors, because Monitor and Merrimack, you don't have that much, I guess, inventivity when it comes to names. This is an example of an early railroad monitor crossing a bridge at the city of Bull Run in spring 1863. In this case, you see that the cannon they have is mounted facing out the side, and is protected by an armored gunport lid, just like on a ship of the line. This cannon would then mean that you can go parallel to an enemy army and just keep on shooting at them while you're going non-stop. Whereas if you have just a forward-facing cannon, once you hit the enemy, you're just kind of stuck. So something like this would be significantly more effective if you also wanted to have several similar rail cars all unloading with their cannons at the enemy at the exact same time, whereas you can only really have one or two guns facing directly forward. Also during the US Civil War, we have the first use of heavy railway-borne siege artillery. This was the Dictator, a 13-inch Seacoast mortar, which was taken from one of the northern shore positions and put onto essentially a railway bogie. It was used at the Siege of Petersburg in July 1864. This particular one was actually cast at Fort Pitt in 1862, so go Pittsburgh, because Fort Pitt was literally where the city of Pittsburgh was founded. The weight of the entire thing was 7.8 tons, caliber was 13 inches, and then the length of the barrel was four calibers. The ammunition was a 100 kilogram shell and 9 kilograms of gunpowder. The first few times that they fired this thing, it actually broke the bogey structure, so they had to repair it, and then they were able to use it for a little bit more. And also during the US Civil War, we have some aerial developments. We have Professor Thaddeus Sobieski Konstantin Lowe, or not professor, because he wasn't actually a professor, he just liked people to call himself a professor. And he was a balloon specialist. So in June 16th of 1861, he became the first man to send a telegraph message from a balloon by essentially taking a telegraph wire, connecting it all the way up to a balloon, and then putting a little Morse code station on board. And this showed that you can do more complicated communications from an aircraft than just like waving your hands around or trying to yell super duper loudly. In September of 1861, he developed the first mobile balloon filling gas generator. Earlier, balloons were typically filled using coal gas from factories, but you couldn't really take it all the way out to a battlefield because normally your factories are far away from the battlefield. What he did was he created several boxes which would be carried on carts and made the whole system very mobile, and he would mix sulfuric acid together with iron filings. This would produce hydrogen gas and then be used to fill the balloon. These balloons had somewhat lower lifetime because there was still some acid that was some acidic fumes that went into the balloon along with the hydrogen, so the balloons got corroded, but they were usable out in the field, which makes them a lot more valuable than a balloon that you can fill but then is just sitting over your city. Once again, also in September of 1861, he performed the very first aerial artillery correction. There was a hidden Union battery at Fort Corcoran, and he was using his balloon with some flag signals to tell them that they've either overshot or undershot, or they need to like fire left or fire right. And within just a few minutes, the artillery battery was able to fire relatively accurately against a Confederate position that they absolutely could not see because they were firing from behind a bunch of woods, hills, rivers, and so on and so forth. And in November of 1861, he performed the first naval air operation because he took a barge and converted it to a ship to carry his balloons. So it had the equipment to fill the balloons on board, and he named the ship USS Washington, George Washington Parke Curtis. I have no idea why. So in principle, this was almost the world's first aircraft carrier, or the first balloon tender. And this particular one he used a few times as he went up and down rivers to report on the movements of the Confederate Army along the various rivers of the Civil War. And also, finally in 1862, at the Battle of Fair Oaks, he was the first person to use balloon observation to basically save an army from encirclement. He realized that the Confederates were planning to launch another attack after they had launched a few attacks. So he had a few balloons at hand, and he used one of them to fill the other one, which was called the Intrepid, a lot faster. And he went up and came right back down and told the commanding officer what was going on. And that information that was provided basically told the general that there was a bunch of Confederates coming in from the left, coming in from the right, but if we retreat now, we still have time. And that particular information allowed the entire army to avoid encirclement. So it was the first time that a balloon observation basically saved an entire army from being destroyed or captured. And unfortunately, right after this, Lowe had gotten very sick, and by the time that he got well, the Union Army decided that they are not interested in balloon observations anymore, so he spent the rest of the Civil War just doing random other operations like for services and stuff. So further military uses of balloons had to wait for a few more decades again. Then going a little bit out of the Civil War and into other developments, we have better naval ammunition. This is Sir William Palliser's shot and shell. This is the first armor-piercing artillery projectile. So motivation was that ironclads were protected by iron, which was basically as good as the cannonballs that were fired against them. So therefore, most of these cannonballs would just bounce right back off. So the solution was then, let's take a shell and make it long so that it's more accurate in being fired. And also, let's make it pointy so that the tip is very, basically is able to nick the armor first. And second of all, let's also harden the tip. So the way that you would harden the tip is when you're casting this shell, you would cast it upside down, and at the very bottom you would have some water cooling in your mold, so that the tip was cooled very, very quickly. And because it was cooled very, very quickly, it became very hard, and because it was hard, it resisted deformation, so it kept its point and its edge as it hit the armor. And then the rest of the shell was cooled slowly so that it was more tough, and it was able to resist bulk fracture. And what this now meant is that the hard tip makes that first initial nick into the armor. It creates a super high stress gradient on the armor, and then once you have that super high stress gradient and you initiate a fracture in the armor, you can then have the rest of the shell follow through and punch through the fracture, and then expand the fracture out, and you can actually punch right through the armor. So a lot of material science and stress analysis going on in the design of a shell. In this case, the shot was cast with an internal cavity, and this was just to make sure that the material is not so thick that it itself begins to crack when you're cooling it down. So it was more of a necessity rather than an engineering design decision. And in the case of the shell rather than the shot, the cavity was itself filled with gunpowder, so that once the shell penetrates through the armor, it then also explodes inside the ship, which causes even more devastation as well. The shell was developed by Palliser in 1863. In 1867, it was adopted by the British Royal Navy, and the first time that it was used in battle was at the Battle of Angamos by Chile in 1879 against the Navy of Peru. This was the War of the Pacific, so essentially people were killing each other over the rights to mine bird poop. And the first time that you were using armor-piercing shells was because you wanted to mine bird poop and not let the other guy mine bird poop. Also, we have the development of the first torpedoes, the first self-propelled torpedoes. The first true torpedo was Robert Whitehead's design, but it was developed from the earlier work that was done by Austro-Hungarian engineers, specifically Giovanni Lupus von Rammer. In 1850, he found some papers written by a different Austrian naval officer that suggested using a boat with a small steam engine on board that would be covered with explosives to be sent against the ship and blow up against the ship. So he took the concept that was presented in the paper and developed it into an actual prototype. In this case, the torpedo was a surface craft rather than just a submerged craft. And with his very first prototype, which was around 1 meter long and had explosives that detonated on contact, the prototype was controlled by very, very long ropes from a coast station because they were unable to come up with an automatic steering mechanism. The second type was also controlled and steered by ropes, but it was given a power plant on board, and it was essentially a very, very powerful spring, just like you would see on a clock, and the spring turned the propeller, and as the propeller swam, you would use a bunch of ropes to control the rudders from a coastal position. The second and last prototype that Rammer was working on was 6 meters long. It had explosives in the stern, and it was detonated not when it impacted, but when it was triggered from a coastal station. So even if you missed the ship, you could still trigger an explosion while it's still close to it. So maybe it could cause some damage instead of no damage at all. And in 1864, Whitehead was invited to help development, which is where he ended up developing his torpedo from. So in 1868, he produced his first Minenschip, which basically means mine ship in German. This torpedo was 3.3 meters long, 355 millimeters in diameter. That ended up being a fairly widely used caliber for torpedoes for a very long while. It had a propulsion based on compressed air and was able to reach a speed of approximately 7 knots. By 1870, it was increased to 17 knots because of better construction. The range was around 650 meters, and depth was adjusted using a pendulum and hydrostat control. So the way that the hydrostat worked is it just measures water pressure. So if you detect that water pressure is increasing, you go closer to the surface. If you notice that it's decreasing, you go a little bit deeper. And the way that the pendulum worked is that if you control your vertical fins, then as the vertical fins turn, a pendulum ends up being turned either left or right, but it wants to come back to center. So in case it's being like pushed or pulled by random motion currents, the pendulum and hydrostat would both take it back to the same depth that you wanted it to be swimming at. And in 1896, he added also course adjustment using a gyroscope. So now, even if the torpedo was like in a current that was trying to turn it, it would fight that current and then turn into the current using that gyroscope. It was first offered for sale in 1868. And when it was offered for sale, there were 2 designs that were offered. One of them was 3.5 meters long and 355 millimeters in diameter. The other one was larger at 4.3 meters long and 406 millimeters in diameter. The license to produce these was bought by Britain in 1871. And the first combat use was in 1878 by Russian Admiral Stepan Makarov in yet another Russo-Turkish war. There were quite a few of them. The Battle of Lissa was a very important development for ironclads. It was the first oceanic battle between ironclad fleets rather than just individual ironclads meeting each other on a river like what happened in the US Civil War, fought in July 20th of 1866. In this case, pretty much all of the ironclads proved that their armor is impervious to gunfire from all of the other ironclads. So both the Italian and the Austro-Hungarian fleets ended up resorting to ramming each other. And in the ramming, 2 ships from the Italian fleet were sunk. And after that, because the naval engineers who were designing future ironclads saw that shells and cannonballs bounce right off, but ramming works. They ended up focusing unreasonably heavily on ramming in quite a few designs. And even though ramming was literally never used as an official way to attack an enemy surface ship, rams were incorporated into most ironclads for the next like 20 years or so. And also because of this, you had a new ship type which appeared, the torpedo ram, which was a very short-lived design because people realized that once they realized that you don't need rams, then you don't really need torpedo rams either. In 1867, France launched the Alma-class ironclad. This was the first warship to be equipped with barbettes. So a barbette is a lighter substitute for a turret. You can see the barbettes right here. So the way that it works is you have a fixed ring-shaped enclosure around the position with the guns. The guns themselves are on a rotating mount. So the way that you would operate is the gun would be raised up above the wall for firing and then lowered back down to be reloaded or stored. And the ammunition, the powder handling were all moved below deck because in a turret, you can put your ammunition inside the turret and the turret is going to keep it safe. But in an open position like this, if you have extra gunpowder and you get hit, all of that gunpowder goes off. So you move all of the ammunition and gunpowder below decks and you just hoist it up as necessary using specialized hoists. And the advantages that a barbette gave you is that You did need to have the very heavy engine that would turn the entire turret, and also you could make, because you didn't have a ceiling, the construction of the barbette itself was lighter than the turret. So this meant that you could take the barbette and place it higher on a ship without fear of the ship capsizing in heavy weather. Also, because you could place the guns higher, you could build the wall of the ship higher, which would then increase seaworthiness, because then it's more difficult for a wave to just flood over the entire deck and then send water into the ship itself. So for quite a few years, and in fact until the 1890s, there was a big debate in naval engineering between what's better, a barbette or a turret. And the final design, which we'll see in the next lecture, was basically a little bit of a combination of both. In 1868, the British launched the HMVS Cerberus, the first breastwork monitor. What the major innovation was here was that you took your turrets and you placed them on a breastwork, which was essentially an elevated superstructure. A turret that is set directly on the deck, just like you saw with a monitor, is very prone to flooding because you cannot truly make a watertight seal around the turret, or at least especially at that time. So if you raise the turret on this short superstructure, then you would make the ship better able to take difficult weather conditions. In this case, the superstructure was only 2 meters tall, but even that was already enough to make it more fit for operation out at sea than just individual rivers. Because, for instance, the monitor itself, it was lost when it got into a storm and it was just flooded over and it sank down like a rock. So in the superstructure that is in this breastwork monitor, it also raises several other sections. So the command bridge is now also raised and placed central. The engine funnels are raised, the living quarters are raised, so everything that you want to make sure definitely doesn't get flooded gets elevated up, and therefore risk of flooding is significantly reduced. This particular guy was 68 meters long and 30 meters in width, and displaced around 93-90 tons, so not particularly big compared to some of the later ships that we're going to see. And in 1871, we have the Devastation class Ironclad, which was essentially taking the concept of the breastwork monitor and then scaling it up quite a bit. So if this guy was almost 3,500 tons, this guy was 13,000 tons, basically 4 times larger. And this particular type of ship is generally regarded to be the grandfather of the battleship. It was the first ocean-going turret-armed ironclad that was fitted with no sails at all. Most of the other ironclads were either very, very small or fit with some amount of sails. On this one, they completely gave up on sails, said that we don't want to take up all the space, let's use it for something more productive. This was also the first major capital ship in terms of a primary ship of a navy that had all of its armament mounted on top of the hull rather than inside of the hull. Because all of the ironclads that came before it either had some or all of the armament still inside the hull, just like a frigate, or else they were very, very small and were not actually considered to be a capital ship. And at the time of its launch, once again, the Devastation was also considered to be the most potent ship in the entire ocean. You can see there is a very prominent ram up in front, because people were obsessed with rams at the time. This guy was 94 meters long and 19 meters in width. Displacement, once again, 13,000 tons. Power, 6,600 horsepower, and speed of around 13 knots as well. Armament consisted of 4 305 millimeter or 12-inch guns. These were the 35-ton rifled muzzleloader, so they were still loaded from the muzzle, and in fact the loading equipment was right below deck in the front. So in order to be reloaded, you had to lower the gun forward, have it be loaded by the gigantic plunger, essentially below decks, and then elevated back up for firing. Armor was 14 inches on the turret, 12 inches on the hull, so this is significantly thicker armor than anything we've seen on hulls before, and also 6 inches on the individual bulkheads that are within the ship itself. Yeah.
What nation developed that ship?
So this was the British.
Oh, okay.
Yeah. Basically, they took their own breastwork monitor, scaled it up, and said, "Hey, let's make a battleship now." Yeah. On the U.S. side, there was some development with lighter ships at this time. The USS Alarm, launched in 1873, was a really convoluted thing with a spar torpedo ram. The ram was very pronounced, as you can see in these photos. And in fact, I believe that this was probably the most extreme ram to rest of the ship size of any ironclad of this particular era. At the very front of this ram, it also had a spar, at the end of which was a spar torpedo. So it could either detonate a spar torpedo, or if that failed, or if you already used it up, you could then ram into things with your gigantic ram. And if that didn't work, up in front here you also had a bow gun. So all armaments going forward, but it was a very small ship, so it was really intended for like small attack runs. In 1874, the British launched the HMS Vesuvius. This was the first ship to be armed with a whitehead torpedo. It was given a single bow-mounted torpedo tube underwater, so the tube itself was underwater, so you couldn't really see when it was launched, when the torpedo was launched. It was developed with a relatively deep hull and fairly low freeboard. The engine room was muffled, and it was initially built without a funnel, and all of the smoke from its coal would be released along the sides. And the reason for that is that it was intended to be a ship to go in night attacks against enemy harbor. So they made it as inconspicuous and quiet as humanly possible. But it never ended up being used in combat. In 1874, also, the US launched the Intrepid, which was the first example of the self-propelled torpedo ram, or the ironclad ram, or ironclad torpedo ram class of ships. This particular one also had its torpedo tube underwater, and in fact mounted in the ram itself. So you could either launch a self-propelled torpedo or ram an enemy ship with the exact same appendage coming out the front. It also had 4 24-pounder howitzers on board as secondary armament. And then in 1876, we have the launch of the HMS Lightning, which is widely considered to be the first true torpedo boat. It was developed for high-speed attacks with just a few torpedoes on board, so not intended to slug it out with giant gunnery ships, just come in, launch its torpedoes, and then go back home, which makes it essentially the real predecessor of both the torpedo boat and the torpedo boat destroyer, which eventually evolved into the destroyer class as a whole. The length of this guy was very, very small, just 33 tons in displacement, essentially just like a pleasure boat, 26 meters long and 3.3 meters in width. Armament initially was 2 355mm whitehead torpedoes, and then eventually it was condensed down to 1, which was in a frontal mounted torpedo tube. In 1876, we have the French launching the Redoutable, the first ironclad built primarily using steel as your construction material. And the advantages that it gave is that steel is lighter and stronger than wrought or cast iron, so it made the ship more protected but also more mobile. You can see that on this particular picture really well that its bottom section is sort of sticking out, and then there's a curve as you go up the deck. This is called the tumble-hove hull. It was more commonly used on wooden ships of the line back in the day, but the French kept the same sort of slope inwards as you go upwards on their ironclads and for their early battleships as well, because if you have a ship wider at the waterline but then narrower at the top, it means that when it's rocking it has less chance of capsizing in heavy weather. This guy was relatively big, almost as big as the Devastation, 95 meters long, 20 meters wide, and basically 9,500 tons. It had a 6,700 horsepower engine. It was a little bit faster at 14.5 knots. Armament consisted of 7 270mm guns, some of which were held in barbettes out the sides. Other ones were held inside essentially hull mounts, and also 6 140mm and 12 37mm guns. We have some developments in submarines as well. We have the French Plongeur in 1863, the first submarine that was propelled underwater by mechanical means instead of just a human cranking some crank very violently. In this case, propulsion was provided by a bunch of compressed air stored in tanks. The compressed air was stored at 12 atmospheres of pressure, and the total internal tank volume was 153 cubic meters. So because of all those tanks that you needed to have mounted on the submarine, it came out to be quite large. It was the largest submarine built up to the time, 45 meters long, 3 meter or almost 4 meters in width, and 400 tons in displacement. It was able to get 4 knots and have a range of 9 kilometers, because compressed air is a horrible way to propel yourself. But at least it was the first example of having something be automatically propelled rather than just essentially use desperate human labor. And this one was also armed with a spar torpedo in the front and also a ram, so that you could do ramming attacks against enemy ships underwater. So sort of like the Nautilus and 20,000 Leagues Under the Sea. In 1867, Narcís Montreal, who was a Spanish engineer, built the Ictineo II. This was the first functional submarine equipped with a steam engine, and in order to make it run, Montreal came up with an air-independent steam engine, which used a bunch of chemicals instead of oxygen from the atmosphere, because if you start using oxygen to burn your coal, you're going to run out of air in your submarine very, very quickly. So he was the inventor of the very first air-independent steam engine specifically for the submarine. He was able to make it 14 meters long, 2 meters in width, displacement 45 tons, not particularly big. He was able to test it to a depth of 30 meters, which was the deepest anybody had gone in a submarine up to that time, and it had a speed of 4.5 knots, which it could support for a couple of hours. And a couple of last notes on artillery developments around this time. In 1862, we have the Debanch breech obturator system. This was the first breech sealing system that was fully able to prevent gas escape and enabled significantly better breech-loaded artillery. In this case, the primary constraint for material was that the sealing material needed to survive high pressure and temperature, but also needed to be soft and deformable so that you could squeeze it against the breech when you're closing the breech. So in the Debanch breech block, you had the following components. You had the interrupted breech plug. You had basically a donut-shaped, grease-impregnated asbestos sealing pad, which was the soft and deformable material which could take high pressure and high temperature. And you had a rounded nose cone, which you can see out here. It was nicknamed the mushroom head because it looks sort of like a mushroom. So the way that this would work is you would seal your breech from the back once you load in the round, and when the round is fired, pressure acts against this mushroom head, and when it acts against the mushroom head, it pushes against this asbestos pad, and that pressure expands out the asbestos pad so that it seals the bore, or seals the breech, and prevents all of the gas, or prevents any gas from escaping. So the exact same system is pretty much used today on many artillery systems. It's just that instead of using asbestos and grease, they use more fitting materials because now we have better materials available. But the principle is basically exactly the same. Another artillery block breech loader mechanism was developed around the same time by the Krupp dynasty. They are the famous German steel makers and also were making German artillery for many, many decades as well. They derived their design from the Armstrong breech block, where you also have a sliding block used to close the breech, but instead of trying to use a screw from the back to seal the block against the breech, they just have a cartridge case which gets placed either behind the round or is just part of the round itself. And in this case, if the cartridge case is sufficiently soft, then during the explosion it expands out and seals the breech itself, so you do not need to worry about doing any sort of external sealing on your own. So in this case, it allows for a significantly faster reload because you don't need to go through the process of closing this breech, pulling it out, like turning it, putting in a new round. You just slide the block out, put in the round, and slide the block right back in. But it does require that your ammunition comes with specialized casing, so it makes the ammunition a little bit more expensive. So depending on what you're designing you're going to do, you might want to use one or the other system. Also, in rocket artillery, there was the Hale rocket developed in 1844. In this case, if you remember previous rockets, they had a very, very long stick behind them that was used as essentially a stabilizer. In this case, he removed the guide rod and instead provided stabilization by using rocket exhaust. And the way that he did it was the rocket had some of the exhaust filtered out or taken out to the side in canted channels. And as the exhaust left those canted channels, it imparted a spin on the rocket, and the rocket was now spin stabilized, so it had better accuracy over long range. Also, because it was no longer trying to pull a gigantic stick behind itself, it had longer range as well because the aerodynamics were better. So in general, this became a more potent type of rocket artillery. And in 1872, we have the Hotchkiss revolving cannon, which basically took the Gatling gun and expanded it to significantly larger dimensions. He had several types in mass production. A 37mm variant, which could fire up to 60 rounds a minute, at least in testing. A 47mm variant with 50 rounds a minute, and this gigantic 53mm variant up to 30 rounds a minute. All of these, really the firing rate was limited by how quickly people could turn the very, very heavy crank and the crank system. He had several different variants made. He had a field variant, which can be seen here, which could be taken out into the field and used against enemy positions. He had a fortification or a naval variant. Both of these would have been similar to this, where it's just installed in some particular location, and you can turn it around, but you don't have to move it on like a gigantic set of wheels. And the naval variant was specifically advertised as being a very good weapon against torpedo boats, because torpedo boats, which were just arriving on the scene right around this time, were very, very light, very fast, very maneuverable. So if you try to train your gigantic guns, the torpedo boat would just be faster than you're able to train the guns on them. So something like this would be a lot more nimble, and therefore it could provide you a defense against these light boats that are attacking with torpedoes. In 1882, we have Colonel K.G. Cook writing a treatise called The Field Artillery Fire from Covered Positions, where the idea of a covered position is that you don't have direct line of sight between your position and the target. So that means that you have to rely on relatively fancy geometry and physics to figure out exactly where the round is going to land. Fire from covered positions was used earlier with mortars and howitzers, but it wasn't so much accurate fire as just lobbing shells over the walls of an enemy city and hoping that they'll land somewhere in the city without really caring where they land. But this was the first treatise that laid out the mathematical and the physical fundamentals for predicting exactly where is your round going to land if you launch it with some velocity, at some angle, and so on and so forth. So very basic physics, but very basic physics applied to a particular specific application. And in 1882, we have the first full metal jacket bullet being developed by Edward Rubin from Switzerland. This was the first FMJ bullet that was developed. Typically, bullets earlier were made out of softer material like lead, and what he did was he encased it in a hard shell of brass or copper. And the reason that he did this is that if you have a very soft bullet and you're loading it automatically by a mechanism, either a semi-automatic or fully automatic firearm, if the bullet gets deformed, it can jam the gun relatively easily. So if it's covered in this hard shell, it makes the bullet more resilient to that type of deformation. Therefore, you have better reliability on your automatic firearm. And in 1866, we have the chassepot, or the rifle model 1866, developed by France. This was improved bolt-action rifle that was somewhat similar to the Dryson needle gun. It was the first bolt-action to see really, really widespread service. There were over 2 million of these made within the time of their production. In 1874, they were converted to use metallic cartridges. So the Dryson gun, for instance, was unable to use metallic cartridges because it was developed for a paper cartridge, whereas this one was more amenable to the improved type of ammunition. And in the design of the chassepot, the big innovation they had was that they introduced a segmented rubber O-ring to serve as the obturator to seal the breech when you're firing. And in fact, it was this design that inspired the Devange artillery obturator, which used asbestos and grease because they were unable to make rubber rings of that particular dimension and that survivability. And that is all.